Thanks, Anna. Yeah, so thanks everyone for coming. It's great to be here. This is my first time at the SF Data Eng meetup, so that sounds good. So I'm going to talk today about the system called Zen that we built at Pinterest, which is our graph storage service. So normally I do this talk with my colleague Shun, but unfortunately he couldn't make it today, so I'm going to do his part. I'm going to try to do as best as I can to the second part of the talk. So usually what I do is I do the overall sort of motivation for this project, the API and the high level design. And then the second part of the talk is a little bit about the internals and learnings from running this in production over the last 1.5 years. So that's the part that Shun normally does, but I'll try to do my best. And feel free to interrupt with questions at any time. It's pretty informal, looks like here, so we'll keep it that way. Just let me know if you have any questions at any time. So a little bit of introduction to how we sort of do engineering at Pinterest. We are pretty early stage. I mean, I guess like not that early stage anymore, but being where we are, we like to iterate a lot on the product, like experiment with a lot of different things, see what works, see what doesn't. And that means that we need to be able to iterate quickly and build products fast. So here's an example of a product that we built last year, which is called Messages, which basically allows you to communicate with other users of Pinterest and send messages to them about some content that you saw on Pinterest. Like, so if you saw a pin that you liked, I don't know how many people use Pinterest. I assume not many in this audience. Cool. Okay, that's good. Nice. Thanks. So if you find something that you like on Pinterest and you wanted to sort of send it to your spouse or a friend, you can, with this product, do it without leaving the Pinterest experience. So it's a pretty compelling, I think, product. And but the cool thing about it is it was actually built from scratch to production, full production launch in 3 months. Here's another product, which is News, which kind of gives you a sense of what people are doing on Pinterest that you're connected to on, say, other social networks or you're following on Pinterest. Kind of get a sense of what they like, what boards they've created, what they have pinned recently, who they're following. So again, like sort of a pretty compelling product. One would imagine not so trivial to build, but this was actually built in about 2 months. So this is something that we like a lot and we want to do consistently. So we ask ourselves, like, how can we do this consistently? And I think it's a little bit about culture, hiring the people with that sort of mindset of building things fast, having small teams that can focus. So a few things around sort of culture, but to us on the infrastructure team, it's like the main thing is to build infrastructure that does not get in the way, because sometimes when you want to move fast, infrastructure can become a bottleneck. And we try really hard to not make that happen, or as often as possible make sure that that's not the case. And actually, like Facebook famously had this motto, it said, move fast and break things. I don't know if you guys noticed, but last year they said, actually they think of it now as move fast with stable infra, which actually resonates with us as well, right? Like, so, yeah, sorry. Yeah, so this is something that we'd like to aspire for as well, like to be able to move fast, but also do it with some level of stability and reliability. And the way we have attempted to do that, and it's worked pretty well so far, I think, is to kind of make it a goal of systems that we build to this notion of move fast to be a goal of systems that we build. So when you build a storage system, you obviously worry about reliability, stability, durability, and so on. But you may not worry so much about sort of like making it super convenient for product engineers to move quickly on top of it. But that's something that we think of sort of a first-class design constraint when we build systems. And we also try to set up teams that span sort of product engineers and infrastructure engineers. So where the infrastructure engineers can focus on the reliability aspect and the product engineers can focus on the user experience. So now let's look at how this approach applies to one aspect of infrastructure, which is persistent storage. Obviously, there's many things in infrastructure, but I'm going to talk today about sort of storage. So let's imagine you're trying to build a product and you're using a distributed database. Like we use HBase and some sort of a sharded MySQL solution at Pinterest. so these databases come with a lot of features, but they're usually key value, and there's a number of things that you end up needing to do. So you need to figure out how to model your data on top of what the database offers. In many cases, there's fault tolerance built into the database, but there's things that you need to do on the application side. You need to be able to do capacity management in sort of a fast-growing environment. Like a product, when it takes off at Pinterest, suddenly scales very quickly. So you need to be able to have a way to add capacity, performance tuning, and things like that. So what we, sort of the first solution that we did to take some of this burden away from our product engineers was, I think, what's sort of pretty common in the industry, which is this notion of storage as a service. So I mean, Amazon offers some of this as well on AWS. But the idea is basically to offer some kind of an API, like we use Thrift as a protocol, RPC protocol within Pinterest. So the idea is to, rather than deal with the database directly, you deal with an abstraction layer on top of the database, which means that sort of behind that abstraction layer, we can do a number of things for you. So things like key partitioning to do effective load balancing. We actually run redundant clusters with some level of failover for higher availability. We do speculative execution to reduce tail latencies, and we can do things like multi-tenancy to get you better efficiency and so on across different use cases. So this was sort of our first step, which was storage as a service, and we found it to be a great step forward. So like our engineers really liked being able to build on top of this sort of abstraction layer rather than dealing with the vagaries of a database and all that stuff. But we asked ourselves, like, can we do even better? Like, can we make it even simpler? And I think to illustrate the problem, here's I just showed the messages product earlier. So if you think of, like, suppose you want to build this product at scale, and the data model would look something like this. Like, you have users that participate in a conversation, and a conversation contains a sequence of messages. And the kinds of queries you would do here is sort of, given a user, give me a list of conversations they're a part of, or let's say, given a conversation, how many users are a part of it, like a count. Or maybe you want give me the most recent messages for a conversation, so that you can display it in some part of the site. So if you look at these kinds of queries, building on top of a key value store is actually non-trivial. You have to build a lot of different tables, build indexes, do some work to keep it consistent. And so what we found is that this is sort of a repeated pattern. And the realization that we had was really these object models, they resemble a graph more than sort of key value. So, and this was true for a lot of features that we build at a sort of a social site like Pinterest. A lot of them are sort of relationships between users and certain objects on the site. And so we found that if you think of it as a graph, and where these objects are nodes in that graph, and they just represent relationships between the objects, it becomes very natural to express some of the operations that I just described as graph queries. And these are very, very simple graph queries, like, given a node, give me some data for that node, give me outgoing edges from that node, or incoming edges, or counts of incoming and outgoing edges. So, so that's basically what Zen is. So Zen is a storage as a service kind of abstraction, but with a graph data model instead of a key value data model. And behind the scenes, it creates all the necessary indexes that you need to support sort of a graph model. It materializes counts separately so that you can query them efficiently. And the first version of Zen has been implemented on top of HBase. But we intentionally sort of designed it to be able to plug in other backends as necessary. In fact, right now we are working on a MySQL backend for Zen. So the idea is that you work with the Zen API. Behind the scenes, we'll kind of use HBase or MySQL depending on various needs, depending on your workload and so on, and what works best for us longer term. So one thing I want to clarify is what Zen is not. It's not a full-fledged sort of graph database. So there are graph databases out there, and so one of the questions we get is, why not use, say, Neo4j or something like that? But So that's not what Zen is. It's not meant for advanced graph operations like say depth first search or random walks or anything like that. It's really sort of a more convenient way of modeling your data rather than key value. And the key thing is it's built on top of existing databases. So we know how to operate HBase and MySQL at scale, at very large scale at Pinterest. We know how to do backups, durability, failover, availability, and so on. We love that, and we just like a convenient abstraction on top of it that product engineers can use to write code fast. So that's really what Zen is. So with that, I'll go into the API. But any questions so far? Does that make sense? Yes.
You mentioned that it supports multiple backends. What kind of features does the underlying database need to have in order to be able to put them on top of it?
Yeah, so that's a very good question. It's just pretty much key value. So you'll see our data model in a little bit. It's a sort of a distributed key value database. So like as long as you have something that meets that, and obviously durability and things like that. But so we have something like say RocksDB or something wouldn't work without a lot of work to add replication and things like that. But any distributed sort of key value database, in theory, you can plug in as a backend to Zen. Memcache, yes, in theory. So if you don't want durability, you could build it on top of Memcache as well, yes.
Yeah. Do you do the key partitioning yourself?
Key partitioning, yes. Yeah, I'll talk a little bit about the HBase, sort of how we model this data on top of HBase. Cool. So very quickly on the Zen API, it's pretty simple once you sort of get that sort of graph data model. So you have nodes. You can do the basic CRUD operations on nodes: add, remove, get. Nodes are referenced by globally unique 64-bit integers called node IDs. So these are generated by Zen. Whenever you create a node, you'll get a node ID back. The data that you associate with nodes are in the form of these key value pairs called properties. So they're simply like sort of string to arbitrary byte values. And I'll talk a little bit later into why we model data this way in terms of sort of properties. And then there's edges. Again, you can do sort of basic CRUD operations on edges. You can also attach property to edges, just like you can attach property to nodes. Edges don't have unique IDs. They're referenced by the from node ID, the to node ID, and an edge type. So there can be only one edge of a certain type between a pair of nodes. All edges in Zen are directed, and you can query them from both directions. So I'll get to that in a second. There's also a score associated with each edge that whenever you're retrieving a list of edges, you can retrieve them by that score, sorted by that score. So that's, just think of sort of when you want to get all the messages for a conversation, you might want to get them in reverse chronological order or something like that. So then you would use score to order them in that way. And then there's this the multi-edge queries. So essentially you specify the query as a node ID, an edge direction like incoming or outgoing, and an edge type. Once you have these three pieces of information, you can do get edge queries, you can do counts, you can do remove edges. All of this works the same way. And when you do get edge, the edges are retrieved in score order, as I said, and they're also paginated in the sense that you can sort of do the limit offset model of retrieving pages of edges up to millions of how many ever you want. There's one other feature in Zen which we found to be pretty useful is this notion of property indexes, and this is why we have the data modeled in the form of this key value pairs called properties. What you can do is you can attach certain attributes to these properties. So you can say this property has a unique index attribute. What that means is that Zen will ensure that the value of that property is unique across all nodes or edges of that type. And I'll give an example of each of these in a couple of slides. But a non-unique index is just a way of sort of retrieving nodes or edges by the value of a property. So give me all nodes which have property foo equals bar or whatever, right? Like, so you can do things like that. And this works for both nodes and edges because you have data associated with both nodes and edges. So Zen as a type system kind of at a very very loose sort of type system, so you don't have to declare. Yeah, so whenever you add a node or edge to a Zen cluster, you need to declare the type in advance. You don't need to declare each and every property, so it's free schema, so you can add as many properties as you wish. But obviously you need to tell us which properties you want unique and non-unique index attributes on. So you specify that through the type schema. The type schema is fully online. There's no deploy or config. There's an API for it. You can add types. And actually we implemented that on top of Zen itself, so it's kind of interesting. So hopefully this will give an idea of how you would use Zen, right? Like, so if you want to build the messages product that I showed earlier with that data model, what you would do is you would create 3 node types, so user, conversation, and message, and 2 edge types, participates and contains. You would add some properties to each of these nodes, and that's it. Like, so pretty much you're done at that point, and all the queries that we talked about earlier essentially work out of the box. So things like, given a user, give me the list of conversations or counts or in either direction, like all of those queries that we talked about earlier just work. There's also an example here of the unique and non-unique index attributes. So let's say I wanted to ensure that usernames are unique across all nodes of type user. All I do is attach the unique index attribute to the name property, and Zen will ensure that. And let's say I want to, like, these conversations are really about pins on Pinterest. So there's a pin ID property with each conversation. Now let's say I want to do a query which says, given a pin ID 10,001, give me all the conversations that are about that pin. So like when you view a pin in Pinterest, you might want to show what people are talking about it. So all you do is you attach this non-unique index attribute to that pin ID property, and you can do that query. And you basically are able to retrieve all the conversations, again, in a paginated way and everything. So that's sort of the basic data model of Zen. And so we built this in fall of 2013, roughly, so about 1.5 years back. And so since then, actually, it's worked out pretty well. And almost every large product feature in Pinterest that's been launched since then has used Zen in some fashion. So for example, Smart Feed, which is our current version of our home feed system. Messages, which I talked about, network news, our interest graph is modeled on top of Zen. Several other upcoming features are built on this. So the numbers given here are a little bit dated, but yeah, so we have about 10 clusters doing an aggregate hundreds of thousands of requests per second. Many of these are large batch requests, like you retrieve edges in batches or you add edges in batches. So in terms of HBase operations, it comes to over 5 million every second. So it's running at pretty large scale at Pinterest. It's worked pretty well for us. So after this, so it says Shun there. I'm going to be virtual Shun. So I'm going to talk a little bit about the internals and learnings from running this in production. Before I get into that, any other questions so far about the API or?
How big is your cluster? You say 10 clusters?
Okay, yeah. So the question was how big are these clusters? So that's a good question. They vary quite a bit in size. Some are, I think, 50 nodes. Some are 200 nodes, 300 nodes, and by nodes I mean EC2 instances. Yeah, so it depends on the use case. We have kind of a main cluster that's multi-tenant. So when new users come in, we kind of onboard them onto the main cluster. But when there are really large use cases, we separate them out, or something that needs real heavy isolation, or I'm going to talk about some storage system level tuning that we have done for some specific use cases. So when we need to do that, we isolate them into different clusters. Yeah.
I was curious, since the storage backend is basically any key value, and you were talking about Mooncache a little bit, you guys are using HBase, which is very different, kind of the opposite. I'm wondering, like, how big do the keys get that you're dealing with, right? I'm imagining you're keeping indexes as keys.
Yeah.
I'm just wondering, like, kind of what is the space of, like, how big the values get to how many, and I'm sure you have different record sizes.
Yeah.
Offsite question about that.
Sure. That's actually a good question. So the question is, how big are the keys and values? So the keys are sort of within our control, and I'll talk about in the data model. I'm going to show what the keys are. So they're usually relatively small. The values can be arbitrarily large. And that actually, I think the question on about using different backends, yes. So I think when you use a certain backend, there might be constraints. So for example, as we are building the MySQL backend, completely free schema is no longer possible. Like you need to, in some sense, define your properties in advance. With HBase, we have the ability to add whatever properties you want. So yeah, I suspect that will be sort of an issue. Is like depending on which backend you use, there are certain limitations that you might run into. But with HBase, in terms of values, there's no real limitation. You can be pretty large.
Right.
Yeah.
Obviously, that's why I was like, it seems like technically you can use it on any key value store.
Yes.
But in many cases, you'd be limited because it's hard to quote an exact thing, but like Mooncache just performs poorly.
Yes. Good point.
But obviously, I mean, a small test case.
Yeah.
That would probably be the main.
Yeah. Cool. Yeah.
How did you test the load?
How do you test the load? You mean for the Zen system or?
For the writes, the requests.
Oh, how do I get that number there? Or, oh, we have a lot of metrics. So we have a sort of a metrics collection system at Pinterest, and all of our services export metrics and sort of and yeah, so our metrics collection system. So we have dashboards and so on which show how much QPS we're doing at any instant of time. Yep.
You said something at the beginning that I thought was actually really interesting, and something I've never heard before. So when you're considering creating this system, it sounds like you guys took in the heavy account, well, we could introduce a new thing to maintain operationally, like Neo4j,
Yeah.
but we know operationally how to do a HBase, we know how to operationally do a
Yeah.
MySQL and deploy. So instead of putting more load on the outside of our house and all that stuff over there, we're just
Yeah.
going to build a service that kind of can use those data stores.
Yeah.
How kind of early in the development process did you start thinking about that? Like what kind of debates went in that? Because one can always obviously argue, well, you can have a deploy mechanism, easy metrics monitoring systems you can plug into,
Yeah.
stick Neo4j in that, and basically if you improve kind of the infrastructure and ops portion of the things, then it's not that difficult to introduce a new back in the store.
Yeah.
Just kind of the trade-offs and how you ended up deciding to go with rolling your own on top of the stuff you're operationally.
Sure. Yeah. So the question is, how did we sort of come up with the decision of potentially introducing a new database and taking some of the operational work to get that database in production versus building on top of database that we know and doing all the work to do a graph data model on top of it? That's a very good question. So I think there's a few answers to that. So one is Neo4j strikes me as, I have not used it very closely, but it strikes me as sort of meant to do graph operations themselves, right? Like things like I actually have a large graph of PageRank or some kind of a graph computation. So our use cases were really not that way. So they were just product features that were being built and needed to work at very, very high, large scale, at very high throughput, very low latency in an online user-facing way, and not sort of offline computations. But we found sort of modeling your data, thinking of your data in form of a graph was useful. And so if you take something like Neo4j and put it in the scale that we're talking about, I think it would have been a bit of a challenge to sort of work at that scale and for that type of online user-facing use case where latencies are important and we need to do a lot of storage engine level tuning. I'll give an example of that. And so yeah, so I think we felt, and in fact like the HBase backend that I'll talk about is pretty simple. Shun was a really good engineer, but yeah, he built this in a month. So the HBase backend for it. So it didn't take that much effort, and obviously over time we have added a lot of work to it. But yeah, hope that answers your question. Yep.
How did you get your performance metrics to compare against say Neo4j or any other options?
Yeah, so Neo4j, I think we didn't do a performance test specifically. We did do some load tests initially to make sure that HBase would work for us. We are now building the MySQL backend, and we are doing some load tests there as well. We obviously compared with existing systems that we have, key value storage systems on top of which people have built products on, and we also use Redis, and yeah, so we looked at a few different options, did load tests, and HBase was already running at pretty large scale and at Pinterest, so it was sort of a natural first choice. That's why we picked it. Yeah.
How eventually can reflect your level of technology and
Okay, so the question is, how is a cluster defined? Yeah, cluster is sort of a group of nodes, sort of one HBase backend with some stateless thrift server machines in front of it. That's sort of logically distinct from another HBase cluster. So it's kind of like clusters in the storage system level. And the Zen aspect of it is just sort of a thrift service or some service like a Java service, in fact, in our case, running on top of HBase. So it's just sort of isolation in terms of machines and yeah. So yeah, I don't know if that answers your question.
So they are all still contained. They don't have nodes related to other nodes.
Yes, so the clusters don't talk to each other. Obviously, applications are sometimes built to talk to multiple Zen clusters depending on what they're doing. But yeah, so a Zen cluster is self-contained. Yeah. Cool. So yeah, so let me go into a little bit of the internals of Zen. So yeah, I think we covered this a bit. So we built a HBase backend. We're working on a MySQL backend. How many people are familiar with the HBase data model? Okay, a few people. So I'll just quickly go over the data model because that'll put the other part of the talk in the context. So I mean, essentially HBase is modeled on Google's Big Table. It's I think what they call a large sorted distributed sparse hash map, and essentially you have rows and columns. Columns are contained within groups called column families. So for example, data is a column family here. It has a couple of columns and we have one row with a couple of values. Here's another row with a third column. You can add these columns sort of on demand at will. Not every cell needs to be populated. That's where the sparse aspect comes from. Yeah, so that's all. It's just pretty simple sort of key value with the notion of columns and column families. So given that sort of, okay, let's look at each part of Zen and very quickly look at how we would model the Zen data on top of HBase. So the first thing is properties. So some properties are built in, like say score for edges or type for both edges and nodes. And then you can have your own custom properties like name and distance in this case. So the way this is stored is, yeah, so each property is a column in HBase and the row is either a node ID or an edge reference. An edge reference being from node ID type to node ID. So that uniquely identifies an edge. So I think this answers the question around like the sizes of row keys. It's usually pretty small because it's totally in our control. And column names are the property names and the value in the cell is the value of the property. So that's sort of a very simple way of modeling properties in Zen. The property index, so as I mentioned earlier, so there's the unique and the non-unique index. So the way the unique index works is it's a row that contains the node or edge type, the property name and the property value. So you have the 10 name equals Ben Smith. So that's the thing that you have an index on. And for the unique index, the node ID is inside the cell. And you use a cas operation when you create it, and this ensures that it's unique, right? So that's how the unique index works. With a non-unique index, it's very similar, but you actually put the ID in as part of the row key, and the cell itself is empty. And this way you can do a scan and retrieve all the node IDs that are part of that index. Does that make sense? So, and the one other thing is you have a hash of the sort of everything except the ID part of the row key. We take a hash and prepend it to the key. The reason to do that is basically to get some kind of balance. So balance sort of indexes across HBase regions. Because otherwise what would happen if you didn't do the hash is if a particular index is very popular, it could be that all of that index is located in one region and you would have a hotspot. And so we kind of use this hash trick to reduce that. I'm sure a lot of you have done things like that before. So the edge score index, which retrieves edges from a node, is very similar, except that there's a score component there, which is highlighted in yellow. And the score gives you the ordering, and there's a sort of intentionally before the node ID there to give you that ordering. So pretty simple. And count again, yeah, so given a node ID, an edge direction, and the type, we store a count. So again, it's pretty simple. So it's a pretty simple data model. I think this covers the basics of it. And as I said, like I think we were able to build this in about a month, and of course took a while to get the production performance and so on out of it. So now I'll talk about a little bit about some of the things that we had to do over the last year as more products came on, were built on top of Zen, and some of the new features we needed to add, and performance tuning that we needed to do. But so you had a question? Yeah. No, so I think, yeah, so this, the edge score index is usually small, so it's all the edges that are associated with a particular node. So those could go in the millions in the rare cases, but yeah, it's not going to go into tens of millions or something like that. So yeah, we don't use the hash for the edge score index. Whereas, yeah. Sorry, so what's the question?
I was going to ask, you are mentioning how do you sort, how do you get the sort?
Oh.
Not
Oh, over here? Oh yeah, so the question is, I think if you have a hash prefix, how are you able to scan? And so the hash prefix is only on this part of the row key, so not on the last part, which is the variable part. So essentially for a given property name and value, for a particular value, so in this case like last name equals Smith, you will be in the same region, and all the node IDs associated with that index. So yeah, and a particular property value is all in one place, but different property values are in different regions. So that's how it works. Yes?
So it goes in reverse order when it's storing keys?
Yeah, so I think it's an ascending order of that, the score or whatever is on the right side there. In this case, it's a node ID. We actually added a feature later to do descending scores as well. But yeah, the thing you cannot do in HBase is like you cannot scan in the other direction. You can only scan in one direction.
And also, can you ask the question how many nodes are pointing at this node?
Yes, so the question is, can you ask how many nodes are pointing at this node? Yes, so we materialize, these indexes are built in both sides of the edge, for incoming and outgoing. And in fact, I think, yeah, if you see the edge score index, it says out and in there. So that basically means an outgoing edge or an incoming edge. So yes. Any other questions on the data model? Cool. So yeah, in terms of new features that we needed to add, this one is basically something, I mean, yeah, soft delete is probably obvious to anyone who's using database, but the idea was like people wanted to be able to delete nodes, but keep the relationships so that in case you need to undelete. For like, a good example of that is if you store user objects inside Zen, and sometimes you deactivate users for like either the user deactivates themselves or like because for spam or something like that, but you need to be able to reactivate if you want, and then you're able to reactivate and retrieve all the edge relationships that you had. So this one is a little bit interesting also. We found for performance reasons, clients used to sometimes retrieve data from Zen and then cache it in memcache or somewhere else. We said we'll add a cache. It's actually an intern project last summer. We'll add a cache inside Zen, which gives you, basically we're able to say, what performance do you need? We'll get it for you with some combination of cache and a backend database, rather than the client having to do caching on their own. So this is something that we found useful. We added a feature called namespaces, kind of gives you the ability to partition certain data sets that are not related into different HBase tables. The goal there is essentially you can move from one cluster to another. If we need to, we can do tuning for a use case specific case, like so in some, like let's say the data in namespace 1 needs to be tuned at the storage engine in a different way from the one in namespace 2, we're able to do things like that. And a number of other smaller features, things like online type schema change, making some of the features optional. Not everyone needed edges materialized on both directions. So if you don't want to pay for, if you don't need it, you don't need to pay for it. You can make it, you can remove it. Edge counts. If you don't want to do it, you don't need to pay for it. Retrieval of subset of properties. So like I want to, rather than all properties, things like that. So descending edge score for convenience. And I'll talk a little bit quickly about some of the performance challenges that we had and how we try to solve it. This particularly, I think, was for the smart feed, home feed workload. So the home feed basically is a system which is sort of push-based home feed. Like whenever someone creates a pin, we fan out that pin to all the people that follow that pinner. Pinner is a user of Pinterest. So this is a very, very demanding workload with doing 1 million edge inserts per second and so on. So what we found when we first put this workload on top of Zen is that the bottleneck was kind of HLog flushes. So each time you do a write into HBase, it has to do update a write ahead log, which is an HDFS. So that became a bottleneck in performance. So the way we solve that is pretty simple, like pretty obvious, which is using batching. One approach to batching was on the client side, you insert edges in bulk rather than one at a time. But you also had the ability to do batching on the Zen server itself, which is this notion of sort of group commit. You buffer edits for a while and then commit them together and acknowledge back together. So this reduced HLog flushes by orders of magnitude and got this workload working out for us on top of Zen. Then there are tricks around memory and performance within the HBase storage model. So HBase uses Bloom filters to reduce disk seeks, but there are cases when you don't need a Bloom filter. So if you're not doing random lookups, you don't need a Bloom filter, and we were able to save memory for other users by actually removing the Bloom filter. So the Bloom filter is meant to be sort of a small data structure, but in fact in HBase the cost is 1 byte per row, which is not trivial. It can be pretty large. So if you don't need it, you can disable the Bloom filter. It gives you more memory for the block cache for HBase. So yeah, a little bit of details in terms of HBase, tuning of block sizes, tweaking the encoding and compression. So I think by default HBase has fast diff encoding and snappy compression, but for certain super high write heavy workloads, we found that this was very CPU expensive in terms when you're doing compactions and major compactions. So we sort of disabled compression and used prefix encoding, and that worked better. Things like that. So a lot of small things going in deeper into the HBase storage engine. And the reason, as I mentioned earlier, we were able to do this is because of namespaces and cluster isolation. So we could isolate certain use cases and tune the hell out of those when we need to. So the last thing I want to talk about is data consistency. I'm sure some of you wondered when I talked about the data model, what about data consistency? So when you add an edge into Zen, there are all these operations that need to happen. So you need to create the indexes, you need to add the properties, add those score indexes in both directions, materialize counts. All of these are separate HBase operations. So the question was, how do you get consistency? And when I mean consistency, I don't mean in the database level. Obviously, HBase itself is strongly consistent across replicas, but it's really consistency between all these different tables and the core data in the indexes. So the question was, if you want strong consistency, we could do it through some sort of a distributed transaction. And I think there are implementations out there on top of HBase to do distributed transactions. But obviously they come with a huge performance cost, and that wouldn't work for us at our scale. So what we did is essentially offer sort of a relaxed consistency model, I think similar to what Facebook does for similar systems that they have. Basically our applications can tolerate some small level of inconsistency. Like, so for example, if the count is off by 1, it's not the end of the world for most of our use cases. So we were able to focus on performance. Yet we did our best to reduce inconsistencies and tackle them. So things like when you do this sequence of operations and something fails, we do manual rollback in the Zen server. So tricks like that help you reduce some of the inconsistencies, but not completely get rid of them. So we have offline jobs, which we call Dr. Zen in this case, to periodically scan the whole cluster and fix inconsistencies. And we also have tools to do one-off inconsistency fixes. So some of the future work, so we are continuing to iterate on Dr. Zen. We are, as I mentioned earlier, adding other backends. We want to look into doing distributed transactions for use cases that need strong consistency and are willing to pay for it with performance. And finally, later this year, we want to open source Zen. So it's kind of like there's a good point in the life cycle where you can think of open sourcing. And at this point, Zen is pretty mature, but we are still iterating on it. In a few months, I think it'll be a right time to open source it. So we really hope to do that. And yeah, that's it. Thanks a lot. And I'm happy to take any other questions. Yes.
How are you generating globally unique 64-bit IDs?
Yeah, so the question is, how are you generating globally unique 64-bit IDs? So we actually have an ID generation service that uses, there's this thing that Twitter open sourced called, I forgot, Snowflake, yes. So we have something like Snowflake, but we didn't use Snowflake itself because we needed these IDs to be distinct from IDs from another system that we have, but essentially like Snowflake. We have a Snowflake-like service, yes. Yeah.
A less technical question. So at the beginning of your speech, you talked about how you all have just like to iterate quickly and find out if it's working.
Yeah.
And I was curious, at what point does a small team of interest cut a project? If you don't cut the project during an iteration, what's the trigger to tell you to pursue this further? Can you talk about that?
Sure, yeah. So the question is, when we iterate quickly, at what point would you decide to cut a certain project or a feature? So that's a very good question, and I think we are sort of trying to figure that out. Like, I don't think we have a, yes, this is the way we do it. It kind of varies from project to project. But Pinterest tends to be usually very data driven. So we typically try to build something quickly. And things like Zen allow you to do that, but also in some cases you hack together some solution and launch a product as sort of a small experiment. And then if you see the data that it's working out well and it seems to be adopted well, then you usually end up building more robust infrastructure and sort of building it at larger scale, or you give up. So I think, yeah, it's more an art than a science. I think there's no exact formula, but usually data tells you very quickly whether it's working or not. And of course, there's a piece of iterating as well. Like, so sometimes it doesn't work in the first iteration, then you iterate a little bit, but at some point you decide, let's cut this and move on. Yeah.
So you mentioned with namespaces.
Yeah.
Like, are there just a few large HBase tables, or are there multiple tables per application or per feature?
Yes. So the question is, are there a few large HBase tables or multiple tables? So yeah, literally the tables that I showed there in that namespace slide are all there are. Like, yeah, so there are like 3 or 4 tables per. Yeah. So yeah, Zen uses a very small number of tables, something like this, or maybe like one more table, but that's it. Yes. So there are a very small number of tables per namespace. Cool. Any other questions? Yes.
Did you consider maybe going to like a optimized HBase, like MapR M7, or are you just doing Apache?
Yeah. So the question is, did we look into using some kind of optimized HBase from MapR, or no? So we are right now using a stock sort of HBase in open source. We have a number of patches and so on. There's actually a talk, I think, on YouTube by one of our engineers about how we got HBase working in an online sort of user-facing way. Like, I think, as many of you know, HBase largely has been used in the analytics and sort of offline world outside of sort of a few companies. So things like mean time to recovery. So there's a bunch of work that we put into HBase that we also want to open source at some point. In order to get it working for online sort of user-facing workload. So Yeah, so yeah, we haven't tried any of the optimized HBase releases, I guess. Yes.
You stated that a lot of folks initially when they're using Zen use their own cache on the client side, maybe
Yeah.
cache, and that you then put a cache in front of Zen.
Yeah.
What were kind of how's that designed? Because obviously the cache LRU, right, it's just a global namespace of keys.
Yeah.
You have LRU semantics across the entire thing, but you have a Zen server, so Zen cluster serving one kind of possibly disparate use cases.
Yeah.
Any challenges in doing that and kind of how did you do that?
Cool. Yeah, so the question is, how did you design a cache for this kind of data set? That's a very good question. So the first version of the cache that our intern built was actually on top of Redis. So Redis actually offers you some data structures that make it more convenient to do things like edge lists. So obviously the properties of Zen are just key value, so you can cache those pretty easily. That was the first thing that people wanted to cache. Counts are also very easy to cache. And in terms of negative queries, HBase is already good with it. So really the challenge is in caching edge lists, and you can do that in Memcache. And in fact, we ended up moving from Redis to Memcache for other reasons more recently. But yes, the original implementation was on using a Redis sorted set, which made it very easy to do edge lists. But we do have the ability, sort of list-based caches on top of Memcache, but yes, they are a little less efficient and convenient to use.
Thank you
Cool.
so much.
Yeah, thanks a lot.